So let's do a little bit more with synthetic division here. Given the function f of x, use synthetic division to find f of negative 3. We just learned the remainder theorem, and the remainder theorem tells us that if we do synthetic division, the remainder r is equal to f of k. In other words, f of k is equal to the remainder of our synthetic division. So in this case, our k value would be negative 3, and we could set up our synthetic division by putting down our coefficients of each of our individual terms, drawing in our synthetic division box, and putting our value of k on the outside. So recall that to do synthetic division, we add vertically, and then we multiply diagonally to get to the next position. Bring down the 5. 5 times a negative 3 gives me negative 15. Adding vertically gives me a positive 3. 3 times a negative 3 gives me a negative 9. Adding vertically gives me negative 2. Negative 2 times a negative 3 gives me a positive 6. And adding vertically gives me 0. 0 is our remainder. So according to the remainder theorem, f of k is equal to r, the remainder, which means in this particular case, f of negative 3 is going to equal 0. And we could easily verify that by plugging in negative 3 into our function. If you were to plug in negative 3 for x into this function, you would indeed get out 0. Now, there is something extra special about this case. If the remainder is 0, like we see here, the factor theorem says that when a polynomial is divided by x minus k and the remainder is 0, x minus k is a factor of our function f of x. This also means that f of k is equal to 0. And again, that's what we just found here. F of k is equal to 0. F of k equals r, the remainder. And that the ordered pair k comma 0 is an x-intercept of the graph. Remember that zeros and x-intercepts are synonymous. They mean the exact same thing. So let's talk a little bit more about this x minus k is a factor. Why is that the case? Well, consider the division that we actually just completed. We took the polynomial 5x cubed plus 18x squared plus 7x minus 6. And doing synthetic division means that our divisor, what we were dividing by, was in the form of x minus k. In other words, we took this polynomial and we divided it by x plus 3. 5x cubed plus 18x squared plus 7x minus 6 divided by x plus 3. And what we got for our quotient was 5x squared plus 3x minus 2. Notice each of those numbers is coming from the values that we ended up with here with our synthetic division. So here we have this equation, and you might notice that the numerator of the left-hand side of this equation is equal to my original function f of x. If we wanted to isolate the numerator, our original function f of x, in this equation, we could manipulate it by multiplying both sides of the equation by x plus 3. Doing so would give us 5x cubed plus 18x squared plus 7x minus 6, our original function f of x, is equal to the quantity 5x squared plus 3x minus 2 times x plus 3. Again, notice this equal sign. These two expressions are identical. Here on the left, I have my polynomial written in its polynomial form, the original function in polynomial form. And here on the right, I have a factored version of that exact same polynomial. We were able to use synthetic division here to factor out x plus 3. X plus 3 is a factor of our original function f of x. Wow, that is so important because we took what would normally be a very difficult polynomial to factor, and we were able to use synthetic division to break it down and figure out that x plus 3 was a factor, leaving us now with a quadratic factor times this linear factor. So the factor theorem again says that when a polynomial is divided by x minus k, and it's always a good idea to use synthetic division to do that, and the remainder is 0, that means x minus k is a factor. And in this case, x plus 3, again, that's x minus k, x minus a minus 3, we can see is a factor of 5x cubed plus 18x squared plus 7x minus 6. So using synthetic division to help us factor polynomials is going to be a very, very useful tool. Let's see if we can't put it to use in another problem. Use synthetic division to show that x equals negative 4 is the solution of the equation x cubed minus 28x minus 48 is equal to 0. Use the result to factor the polynomial completely and find all the real solutions of the equation. So if x equals negative 4 is a solution, that means that if I were to do my synthetic division out, I should get out 0 as my remainder. Okay? Remember, this is x is equal to k. Our divisor, our synthetic division, would be x minus k. So our k value in this case, that's going to go on the outside of our synthetic division. X equals k. K is going to be negative 4. On the inside of our synthetic division, I'm going to put each of our coefficients. Notice that I have a placeholder for my x squared term, which is missing. This would be 1x cubed plus 0x squared minus 28x minus 48. And I draw my synthetic division box and put my value of k on the outside. In synthetic division, we add vertically. We bring down the 1. Multiply by k to go to the next diagonal position. That would be negative 4. Adding vertically, we get negative 4. Negative 4 times a negative 4 gives me 16. Adding vertically, we end up with negative 12. Negative 12 times a negative 4, that gives me a positive 48. And a negative 48 plus a 48 is going to give us 0 for our remainder. All right, so what we just found is that f of negative 4 is equal to 0. If we were to plug in negative 4 for x into this cubic polynomial, we would indeed get out 0. That means that negative 4, x equals negative 4, is a solution to this equation. All right, our remainder being 0 shows that x equals negative 4 is a solution. So let's think about the division that we actually just completed. We just took x cubed minus 28x minus 48, excuse me, and we divided it by our divisor. Remember, the divisor for synthetic division is in the form of x minus k. Well, if k is negative 4, that means we actually took x cubed minus 28x minus 48 and divided it by x plus 4. And what did we get for our solution, our quotient to that division? 1x squared minus 4x minus 12. Again, notice that those values all match up. So on the left-hand side of this equation, the numerator is the cubic polynomial that I have started with in my equation. If I wanted to isolate the numerator of this fraction here, I would have to multiply both sides of the equation by x plus 4. We do a little algebraic manipulation, and that tells me that x cubed minus 28x minus 48 is equal to the quantity of x squared minus 4x minus 12 times the quantity x plus 4. So on the left-hand side of the equation, we have our original cubic polynomial, and on the right-hand side, we have a partially factored form of the exact same polynomial. And so why is this important? Well, this actually allows us to continue to factor. Notice inside of these parentheses, I have an x squared minus 4x minus 12. That is a quadratic that you guys should all be comfortable factoring. And what does it factor into? Well, that factors into an x minus 6 times an x minus 2. And I still have my factor x plus 4. And what we can do is, because we are trying to find all of the zeros, all of the solutions to this equation, is we can set that equal to 0. Notice this is the exact same expression that I started with, Now I just have my polynomial written in a completely factored form. So we can now set each one of the individual factors equal to 0 to solve, and doing so gives us x is equal to 6, x is equal to -2, and x is equal to -4. There we have all of the solutions to our cubic equation. All right, so again, synthetic division allowed us to factor a cubic polynomial that we would normally not otherwise be able to factor. Let's see if we can't try one more. Verify the given factors of the function and use the result to completely factor the polynomial and find all the real zeros. So here we have a quartic that is a fourth degree polynomial, 8x to the fourth minus 14x cubed minus 71x squared minus 10x plus 24. And we are told that x plus 2 is a factor and that x minus 4 is a factor. That means if I take my function and I divide it by x plus 2 and I divide it by x minus 4, I should end up with 0 for my remainder. Each of those factors should divide in evenly. Well, because our factors are in the form of x minus k, we can use synthetic division to verify that they are factors. Notice, again, the factors are in the form x minus k, which means that my first k value would be -2, and my second k value, x minus k, would be 4. So let's start off. We'll do our synthetic division, starting with our k value of -2. Doesn't matter which one you were to pick first, you would get the same final answer, but because our first factor is x plus 2, we'll just start with k is equal to -2. So I'm going to put -2 on the outside of my synthetic division box, and on the inside I have each of my coefficients. This is my 8x to the fourth minus 14x cubed minus 71x squared minus 10x plus 24. Again, synthetic division, we add vertically, bring down the 8. 8 times a -2, that is going to give me a -16. We add vertically, that gives me -30. -30 times -2 is a positive 60. -71 plus 60 gives me -11. -11 times -2 gives me a positive 22. -10 plus 22 gives me a positive 12. 12 times -2 gives me a -24, and 24 plus a -24 gives me 0 for my remainder. So it is absolutely a good thing that we ended up with 0. Getting 0 as a remainder, according to the factor theorem, proves that x minus 2 is a factor. If you didn't get 0 for a remainder, we probably would have made a mistake somewhere, and we would want to go back and check our work. So let's consider the division that we actually just did. We took our polynomial function 8x to the fourth minus 14x cubed minus 71x squared minus 10x plus 24, and we divided it by x plus 2. Again, that's x minus k. And what did we get for our quotient? 8x to the third minus 30x squared minus 11x plus 12. All right, there is our first division. So we just proved that x plus 2 was indeed a factor. Now, let's show that x minus 4 is also a factor. Rather than do our synthetic division from the get-go over again, what we can actually do is continue our synthetic division off of the division that we have already completed. In other words, if x minus 4 is a factor of our original function f of x, that must mean that it is also a factor of our quotient 8x cubed minus 30x squared minus 11x plus 12. So I'm just going to draw out my synthetic division box right below. I put my next value of k on the outside, and I'm going to complete a second round of synthetic division. I bring down the 8. 8 times 4, that gives me 32 in the next location. Adding vertically, I get positive 2. 2 times 4 gives me 8. Adding vertically gives me -3. -3 times 4 gives me a -12. and a 12 plus a negative 12 gives me 0 for my remainder. Again, getting 0 for our remainder, according to the remainder theorem, proves that x minus 4 is indeed a factor. So let's think about the division that we have just completed. Again, we have taken our original polynomial, 8x to the fourth minus 14x cubed minus 71x squared minus 10x plus 24. We divided it first by x plus 2, and in our second round of synthetic division, we divided it by x minus 4. And what we had left over for our quotient was 8x squared plus 2x minus 3. Again, notice those terms come from these values right here in our synthetic division. So how are we going to use this to help us factor? Well, notice that the numerator on the left-hand side of our equation here is our original function f of x. And to isolate our original function, to isolate this numerator, I would have to multiply both sides of the equation by x plus 2 times x minus 4, leaving me with 8x to the fourth minus 14x cubed minus 71x squared minus 10x plus 24, again, that's the original function f of x, is equal to 8x squared plus 2x minus 3, the quantity of that, times x plus 2 times x minus 4. And so here we have our partially factored form. The right-hand side of this equation is our partially factored form of our original function f of x. These two expressions are equal. They are identical. On the left, we have our polynomial form. On the right, we have our partially factored form. So again, we are trying to find the zeros. In finding zeros, we like factored form because if we have the factors, we set each factor equal to 0. We can continue to factor our polynomial now. We have this quadratic, 8x squared plus 2x minus 3. All right, practice your factoring. What does 8x squared plus 2x minus 3 factor into? Well, that factors into 4x plus 3 times 2x minus 1. A little bit trickier with a coefficient that is not equal to 1. All right, but I know you guys can work through it. Check your work after you factor. Notice if we were to FOIL these back out, use the distributive property of multiplication, 4x times 2x, that would give me an 8x squared. I would have a minus 4x, a plus 6x, minus 4x plus 6x would give me a plus 2x, and a plus 3 times a negative 1 gives me a negative 3. So we have indeed factored this correctly, and I still have my x plus 2 and my x minus 4. Now I have our polynomial function f of x written in completely factored form. And because we are finding the zeros, we set the equation equal to 0. And to solve, we just set each of the individual factors equal to 0. Setting each of the individual factors equal to 0 tells us our zeros are going to be x is equal to negative 3/4, x is equal to 1/2, x is equal to negative 2, and x is equal to 4. All right, and so there we have all the zeros of this really complicated quartic polynomial function. So, given a few of the factors, we were able to use synthetic division to divide, which then in turn allowed us to factor the polynomial completely and find the rest of the remaining zeros. All right, so a great skill to have, being able to use synthetic division to factor polynomials. Make sure you understand what you are actually dividing when you complete your synthetic division. Remember, you're taking a polynomial and you are dividing it by a divisor that is in the form of x minus k. All right, our first divisor was x plus 2, and our second divisor, x minus k, was x minus 4. There we have it, finding our zeros by factoring via synthetic division.